Hello, welcome and an excellent evening. And today we want to continue a bit with our Adlib programming experiments. Last two episodes about Adlib we did the percussive mode where you learned how to program the drums on the Adlib. Then we did melodic programming where we could play simple melodies on our PC keyboard and have them play back. But this is, of course, a far-fetched from real music. And before I reinvent musical composer programs, I want to introduce you to this nice program here, the Reality Adlib Tracker by the demo scene group Reality, made in 1995. This is a rather old version, but it has a couple of advantages. It runs on a lowly 286 quite neatly, and instead of the usual tracker programs like Pro Tracker, etc., it doesn't use samples, it uses the OPL2 of the Adlib. So we won't be using our own knowledge that we gained, but we could obviously and code our own player. But the good thing about the Reality Adlib Tracker is that it comes with a simple playback routine programmed in assembly language that you can use in your own programs. It comes with the source code. Everything is fine. So what does this program look like? You can basically load a tune and edit it. You have 9 melodic channels. It doesn't use the percussive mode. Instead, it uses different instruments, which are shown up here. And you can scroll through the instruments. There is a very useful help for everything here, the pattern editor, the instrument editor, etc. That you can call up using the question mark key, and there's a quick help with the most important keys on the F12 key. So there's that. So basically drums are used as melodic instruments. You have different channels that you can turn off and on with the numeric keypad. And you can just simply, I'm gonna turn down the volume a little bit, simply play the whole song, and also for some reason I can't turn on and off now I can turn off the channels. You have to press numlock obviously and listen to single channels, for example. For example, this one here is bassline plus some drums, and channel 2 are more drums, channel 3 as well. So that's how this whole thing works, more or less. A tracker basically stores patterns, which are rows of 64 notes usually. I think 61, 62, 63, yes. Exactly, and it should begin at line 0, so 64 lines with 9 channels. And in every channel you can enter a note like E in octave 2, or it could be E flat or E sharp. And then you have some effect applied. A is, I don't know, you can look that up. There's probably a help in the effect section. So A is a volume slide. It slides either down or it slides up over the next lines. There's also portamento, a frequency slide, pitching up, pitching down, portamento to note, so that you can slide between different notes. And similar things, I have to press plus. Set volume, jump to next pattern in order list to cut a pattern short, set new speed, etc., etc. So this is pretty basic stuff. You can also edit all the variables that we also did for the melodic programming up here in the instrument editor. Arrange all the patterns in a certain order. You can reuse patterns if you have like repeating musical pieces. For example, pattern 4 is used both at position 8 and at position 10. And that's how it works. The whole thing runs on a 50 Hertz timer. There are also a couple of slower, older songs which run on an 80.2 Hertz timer, and why that is, we'll get back to in a minute. But this is basically all that you can do here. and we can quit this and we can have a look. The important thing about the Adlib tracker tunes is that they are tiny. They are really tiny. The biggest one is 18 kilobytes. There are several ones around 2 to 3 kilobytes, and they are still pretty neat songs. Because you don't need to store the samples, you just need to store the parameters for the oscillators. You can have very, very compact music that runs on very slow machines, no mixing by the CPU required. So it's actually pretty neat. As I said, the whole system comes with a player in an assembly file here, player.asm, and there's also a test program, red test, which links together with the assembly code to a redtest.exe, which is fine, and basically shows how to use that. But we want to use C, of course, because we are doing always C programming here. And we can actually load up a program that I prepared. And we will have a look at this in a second and fill in the blanks. But the main idea here would be to take one of the music files, alloyrun.rad, for example, but you could pick any one or compose your own if you are talented musician, load it into memory, then call the assembly procedure init player with a pointer to this music that we just loaded, and it will return an error if it can't pass that thing because it's the wrong version or something, or it will return success, and then we can work on that. And for a first test, we will simply do a busy loop, waiting for the vertical retrace and calling the play music routine, which should be running at 50 Hertz, but as we are running on a VGA card, it will run at 70 Hertz, so too fast. The music will be too fast. And when we press escape, we will be exiting and ending the player. I will show you how to do proper 50 Hertz playback using the programmable interrupt timer in the IBM PC, which you can program freely to produce any kind of frequency, more or less, between 1 and roughly 1.2 million or something. I think it runs at 1.2 megahertz internally or something like that. But that's something that we will have a look at. The load music is actually pretty simple, and I'm not gonna code it from scratch here. We have an in-memory buffer that we're using, which needs to be allocated. We have a file component that will be used for the for opening a file by the given name, which we'll do here, and we will open it in read binary mode because it's a binary file and we want to read it. And if the file returned is null, then there was an error and we return a null buffer, so it can be detected and we can say, oh, can't open the file or something. Then we need to figure out how large the file is, and in standard ANSI C there are no functions for that. But what you can do is you can seek in the file to the last byte by doing fseek on the file object with offset 0 looking from the end. Then you can use ftell to determine the position in the file. The last byte gives you the size of the file. And then we'll seek to the beginning, which you can do with offset 0 and seek set as the origin. Seek set means beginning of file. And then we can allocate memory. We're not using malloc here, but a specific function from the Turbo C DOS header called allocmem. And the reason for that is it gives you memory located exactly on a segment boundary. Segments start off at addresses divisible by 16, and the assembly code actually expects you for the music to be allocated on a segment boundary. So that's what we're doing here and not using malloc. We can still build a proper pointer here by using make far pointer with the segment and offset 0. That's fine. Then we're going to read into this buffer because fread doesn't want a segment but a proper pointer, so we use buff as the pointer, size as determined by ftell, and this is how many bytes, how many objects the size of the objects we are reading. We're reading size times 1 objects, basically byte-wise, from the file. And then we close the file and return the buffer. Very, very simple, actually. And that's that. Let's have a look at the assembly file. The assembly file is in player.asm. I'm gonna go full screen here. I put in my notice here at the top because I rewrote this to better compile with the turbo assembler from Borland. And I haven't finished refactoring this because to make it perfectly fine and clear, we should in theory have 3 different so-called segments in the executable. One should be called code or of type code, one of type data for variables, and one of type BSS for uninitialized variables. However, the original authors put everything into the code segment, and we're also assuming that both the CS register and the DS register for the code segment and data segment both point to the same text code segment. I tried to refactor that, but it's much more complicated than I was expecting. Looking at the very bottom of the file, here is where the code ends. Right before the end are the actual variables, which I wanted to refactor out and into the data segment and the BSS segment, but couldn't. Maybe that's a homework for you to try and do that. And yeah, here are a couple of variables like the Adlib port, instrument pointers into the mod file or the music file. Then there is different values of the registers of the Adlib card that need to be saved. Some basically global variables for the tone sliding and portamento sliding and volume sliding, which is all fine. And then also the segment address basically for the music file. The speed in basically fractions of 50 Hertz of the music, and the counter for deriving the speed, etc, etc, etc. These are uninitialized because they depend on the music file. And that should be happening here. Yeah, that's more or less it, I would say. Pattern list, pattern position line, yeah, that's all fine. One important thing is that I refactored this. This also had no procedures in there, but just labels. I refactored this to use procedures, basically functions. And I declared the init player, end player, and play music to be public and with underscores, so they are callable from C. If you want to call something from Turbo C, the functions are required to have an underscore in front. That's how the C standard prescribes this, basically. And they have to be public, otherwise they're not visible from outside of the object file after assembly. Also, there's a special convention on how to pass arguments around. Let's have a look at the very first thing, the init player routine. It's a far procedure because we are compiling this whole thing in the huge memory model, so we will not run out of memory. Huge just means all the pointers are far by default, or the procedure calls are far by default. And here it still said ES takes the RUT module in memory address, which of course we don't use anymore, but we put it on the stack. That's how C does it. We give it simply an unsigned integer, which is the ES segment address. And the first thing that you need to do in a procedure, in an assembly procedure, is you need to save the stack pointer, stack base pointer, by pushing it to the stack and then moving the current stack pointer into the base pointer, not to mess anything up. And then you can fetch the arguments from the stack. First of all, you will have a far return address because this is a far procedure call, so 4 bytes are already wasted. plus you have the contents of the base pointer that you just pushed. So 6 bytes are gone, and at address BP plus 6, you will have the first argument, which is what we are putting into ES. And this was missing, obviously, from the original code. I added this, and yeah. And the next thing that it does is actually call also the end player routine. If there is any lingering nodes, it will clear them out and make Adlib shut its mouth, basically, and be able to start fresh from a new music piece, basically. And then there's a lot of things happening that you can read at home, but it's basically setting everything up and getting ready, testing. For example, here, if the file starts with AR and DN space, red space, which signifies that this is actually a reality Adlib tracker module, and also the version number is compared, and if anything is wrong, then it will return something in AX, because that's how you return unsigned ints in Turbo-C. If there's an error, it will return 1 in AX, and otherwise it will clear AX and set it to 0, which means no error. At the end, you just have to pop the base pointer again and return, and this will clear up the stack. The end player routine is similar. Since it doesn't manipulate the stack, it doesn't need to do the base pointer manipulation. It just works like so. And it will reset all the voices from the Adlib. That's fine. And the most complex routine is actually the play music routine. It technically should save the base pointer, but I didn't do that. It seems to be working fine either way. Yeah, that should probably have been a nice thing to do, but since it doesn't take any arguments, I think there is no harm done. It will do all the funky stuff and call many other subroutines. So this is actually what needs to be called 50 times per second, which is written here, and which we currently don't do. But first, let's have a last look at how to compile this whole thing. And I think there are still a bunch of ugly Unix line endings here that it doesn't like. I need to redo this, like so. First of all, we are going to assemble the player code and outputting only an object file, which is this /m here. Then we will manually compile the player code that we are implementing, calling the assembly code in the memory model huge, and we are only doing the compilation, so only producing the obj file, because the linking is a bit more complicated than just letting TCC do it. And the why I forgot, maybe that's debug info or something. I forgot, might be. Same here for T-Link. I think the /l is also for debug output, I think. And first thing that you always need to do with T-Link is to link the C runtime startup, and this is called C0 and then a single letter for the memory model. So C0H is for the huge memory model .obj. It's always delivered in the Turbo-C installation directory under lib. And then you link the main program, redplay.obj, also player.obj from the assembly. And then with separate by comma, the output exe file is redplay.exe, and the map file, which we don't need but have to specify anyway. And then any additional libraries. If you're using the math library, for example, we just need the C runtime library, which is ch, again for model huge, .lib. There's also things for compact, small, and similar things. So that's how that works. That's just a batch file. We can type make, and it will at first run the turbo assembly with 3 parcels, because we have forward declarations basically, and it needs to have multiple parcels to know of all the things. Oh, that's actually the /m. Yeah, I do remember. If your assembly file doesn't assemble because it says, oh, there are forward references, then you need to add /m, and it will do 1 or 2 passes to get to know all the declared symbols and things, and then it can actually assemble everything. Then the TurboC compiler is called to produce the writplay.c. We have, of course, a warning because we have empty function stubs still, and then we are linking, which also works. And then we have the writplay.exe, and I'm gonna play it, and you will listen to it and see that it's a bit fast. Okay, that's enough. It's extremely fast because it's like 50% faster than expected, which is of course not what we want. We could do more waiting time here or do a sleep or something, but the issue with that is that will always be very inaccurate. So we are not gonna use the play music routine here, but instead we will introduce a timer interrupt, which is a feature of the IBM PC and many other systems. For that, we will write a interrupt handler function, which in TurboC you do by writing your function signature, which always is returning void and also taking void because it's an interrupt reacting to an interrupt, doesn't take input or output, but it has the interrupt keyword here. We will also have a variable called old timer handler, which is the currently installed interrupt handler, and you have to call this because there might be some important thing like date keeping or maybe some disk cache that regularly checks things, and there's basically a chain of handlers that get called, and the newest one calls the previous one, and so on and so on. So this is where we will store the address of this function. And basically what we can do is inside of a timer interrupt we always have to do or should do a disabled to not be interrupted by any other interrupts and an enable. This is also something that is in the DOS header file. You can look it up. Disable and enable disable all hardware interrupts except the non-maskable interrupt. Same goes for enable, plus the opposite. And inside of this you should do something like old timer handler brackets. But you will see that we will have to change something here. Basically we will call play music and then this, but this will call the new timer handler eventually at 50 Hertz, which is also way too fast. So we will have to do something about that, but we'll see when the time comes. So when we have a look at the help PC website and look at interrupt 1C hex, it's the system timer tick, which is a software interrupt that is actually triggered by a hardware interrupt, namely interrupt 8, which is wired to the 8253 programmable interrupt timer, and there's a documentation on that chip as well, and we'll need that in a second. And usually this thing is called 18.206 times per second, and we will tweak that to be called every 50th of a second with 50 Hertz because that's what writplay wants to have. And yeah, the default interrupt is empty, but you might already have things in there for timekeeping, for example, and we need to call this thing as we've seen. The question is, how do we set a new interrupt basically? That's the function setInt, and in there we need to disable all interrupts as usual so that we don't get any side effects from other interrupts. First of all, we will need to store the old timer interrupt, which is why we created this variable up there. And we can use the getVect function with the timer interrupt 1C set. And this is another thing that you find in the DOS header. There you find the getVect. Pretty simple. The return type, it looks a bit weird because the return type is a pointer to a function. GetVect takes the interrupt number, and the return type is actually enclosing the whole function name, void interrupt pointer to a function. So if you're not used to function pointers in C, it's a bit tricky, but as you've seen, basically a pointer variable to a function looks like return type, and then an asterisk in braces or in parentheses, better said, and then the name of the variable and the parameters that this function takes. As it's an interrupt function, it takes void. And I think, did they specify void here or just empty? I think they probably specified void. Yeah, this is actually a little bit incorrect, but back then I'm not even sure ANSI C was a thing. It probably still was Koenig and Ritchie C. But ANSI C says if you leave that out, it's actually unspecified what parameters go in there. So it's better to write void explicitly. Anyway, this is how we get the old interrupt vector, and we can of course use setVect on the same interrupt with our new timer handler, which is just called timer handler, and the name of the function gives you the pointer to that function. And then we will call another function that we have to implement still, set timer 50, which sets the timer frequency to 50 Hertz. The reset interrupt, we need to clear up the interrupt vector later when we quit the program, so that our code isn't called anymore, because it will not be there anymore. It will be cleaned out by DOS. And here we just call setVect with the timer interrupt and the old timer handler, so to speak. And then we also reset the timer interval that it gets called an appropriate amount of times. And I would even go as far as putting that here, but it shouldn't make much difference. So we need to implement set timer and reset timer. And I've gone ahead and changed the frequencies here. I put 182 before, but we can also work with 18,206, which is a little bit more accurate, so you might experience less drift. Yeah, but let's take a look at the set timer. For that, we need to know a little bit more about the 8253, which is an Intel chip, but there's tons of clones, and in later PCs it's integrated into the chipset. It actually has 3 timer counters, basically, that you can program, and that can produce certain things. It can produce, for example, pulses or square wave pulses. It is, for example, the counter number 2 is used for the speaker, the beeper, and you can produce very interesting sounds with that. Counter number 1 is the refresh counter for the RAM refresh. As the PC and its derived machines are using dynamic RAM, it needs to be refreshed regularly, and the counter that we're interested in is the time of day clock, which is normally running in mode 3, which you can see down here. Mode 3 is set by setting the mode control register, namely the bits 3, 2, and 1, I think, to 0, 1, 1. And what we want to have is basically set this whole thing as follows in the set timer. First of all, we will write to this using the outport byte function. And I've gone ahead and already defined constants. Timer port 0 is port number 40, and the timer mode control is 43, both hexadecimal. So we can write to this timer mode control, and we will select the following, and I'm gonna pull up, can I do that with the calculator? No, that doesn't support binary. So let's quickly grab a hex to binary converter online. Something like this. And let's go and type in 036, and this gives us 00110110. This here is the mode 3. The last bit signifies that we're using a decimal counter, and then we have 0011. Let's look that up. 00 is the counter that we're choosing. Because we're choosing counter 0, we need to put in 00, and then the read-write latch format bits, which are 5 and 4. And we're setting it to read-write LSB followed by write of MSB, because we are going to write the frequency that this thing should have. We need to send a 16-bit value, so we need to do 2 1-byte writes, which means we send first the least significant byte and then the most significant byte. That's how we come to the 0x36 exactly. Then we will write to the timer port 0 the value, which I call counter, which we'll have to specify still, and we will derive it from the input hertz value. And we will take the least significant byte, that is just by using mod, or you could also actually just do an AND. It's the same thing. And we send the most significant byte by doing the same thing. We could either do a diff by 0xf, or you could shift right by 8 or something like that. I stick to this here because I read it somewhere like that. So, but yeah, there's different ways to extract the least and most significant byte. You may pick whatever you like. The interesting part here now is how to program this. In our mode, we generate square waves. We generate 1 pulse after count clock cycles. And does it say somewhere? This is, I think, the frequency in megahertz, I think. Let's see if we can derive this. Here it is. This is the actual frequency that this thing runs at. So to get to 50 hertz, we need to divide this clock frequency, or counter they call it, by the number of hertz that we want to achieve. So we are going to use an unsigned int here, actually an unsigned long int because it's too large for a 16-bit value. I'll call it clock, and that's 1193181 hertz exactly. And we will get an unsigned int out of that, which we'll call counter, and that is the clock divided by the number of desired hertz. This gives us the exact number of ticks until the next pulse happens, which makes sense, I guess, right? So that sets the timer. Resetting the timer works pretty much accordingly. The very same thing here, but we don't need to do complicated things. We can simply set everything to 0 and it will fire in the regular fashion. 18.2 hertz. Okay, that's that. We have the setting of the timer. Yeah, one thing is still missing. We are calling the old timer handler way too often. And that's a bit annoying. We need to call it only when, like, how much is that? We have 50 hertz and we want to achieve 18.206 hertz. I should write it like so, I think. Every 2.746 iterations, which we can't do, but we can do something similar, shifting around the error by taking a time variable, unsigned Let's take a long, I think, because we are almost touching the 16-bit here with this resolution. If we want to have high resolution, unsigned long t, and we will initialize this with 0. This will start off with 0, and as it's a static, it will keep its value in between interrupt calls. And what we'll do is we will increment this by our timer frequency old. So we will add up 18,206. And whenever t gets bigger or equal to timer frequency new, and this will happen on average every 2.74 times, then we will actually call this thing and reset t to 0. This is very simple. The first time it will happen on the third iteration, because 18,206 times 3 is the first value, 54,000 roughly, which is bigger than 50,000. And after that, we reset it. We actually don't set it to 0, but we have to subtract the new timer value and start off with the 4,618. Okay, so that was a little bit of a mistake. We subtract timer frequency new. And so since we were a little bit too early, or too late, basically. Actually, we were too late. We should have happened on the 2.7 iteration, but we happened on the third iteration. We will take this error and push it into the next iteration. And now the iteration will happen a little bit earlier in theory, probably still on the third run. But then on the third interrupt iteration, it will happen on the second try, basically, and so on. And so we will shift around the error. But that is actually it. We have everything here. The only thing that you actually need to have as well to be able to work, you need to define a header with the assembly functions that are made public in the object file and their C signatures without the underscores, because the C compiler will generate the underscore. So our init player function returns an int, and which is passed back in AX, and it takes on the stack an unsigned int with the music segment. End player and play music are both void functions, so there's nothing happening there. And let's quickly check here. We have the old handler, we have the new handler, and it's calling the old handler in the correct amount of time. We are setting the timer using the clock rate divided by the number of hertz that we want to use. We're programming the mode control register and writing out the new counter. Resetting the timer works by setting the mode control to 0 again. And then, other than that, we have the interrupt set routine itself, which stores the old handler, and the reset restores the old handler. And other than that, we have disabled, hopefully, the play music in the wait for retrace loop. And we already have the set interrupt and the reset interrupt. And that should do it. We are freeing the memory and then quitting. Yeah, let's try to see if this will compile. There are no warnings and no errors. Yeah, what's our volume doing? A little bit. There you go. Music is playing. I think it would be possible to do something else here, to run a game, run a demo, whatever. You could even call up a system shell or something and we can work around. Actually, maybe we can do that as an additional thing here. Instead of doing this, let's do the following. We'll comment this out with an if 0, because we have nested comments otherwise. And I think we can just call system, if I remember correctly, or something like that. Maybe not in the DOS file. I will find it. One moment, please. Okay, found it in the process.h, also in standardlib.h, but that is, I think, not part of ANSI, so process.h for MS-DOS. Int system, and I think we can just run command.com, probably. Let's try that actually. System, and then we run command.com. That should hopefully work. Let's include process.h. Illegal command, command.com. Okay, this doesn't work because we're in DOSBox, which is interesting. Okay, we need to run z command.com. Okay, good. Let's do that. Yeah, there we go. We can just move around and do some things. We need to be a bit careful, but for example, we could launch Turbo Pascal. Why not? And have red play running in the background. If we exit, then it's gone. I think that's pretty neat. Yeah, I'm gonna disable that again. But if you want to, you can do something like that. And we are just gonna make this optional. And you can play around with this by putting in 0 or 1 here. And that should do the trick. Yeah, I think that's it for today. Take the source code, play around with it, and make some great music in Reality Adlib Tracker. And share, like, and subscribe, the usual things. Thanks a lot to my patrons who support me in a spectacular fashion. And yeah, share your thoughts, your comments in the comment section below. And I'll see you in the next video. Bye!